Hello again, I hope you're doing well. And for today, we are going to continue from where we left in the previous class. I remember in our previous class, we did this level, which is counting signals, whereby we were able to detect odd numbers of signals, even number of signals, and basically we can detect anything we want based on the signals. And for today, we're going to continue on creating a half adder. Usually a half adder, from the name, is something that is able to do addition. It's a circuit that is able to do an addition. A half adder is a fundamental combination logic in digital electronics, designed to add two single bits, binary numbers, typically A and B. It produces two outputs, which is the sum of that and a carry. Usually, when we do an operation, just a normal operation using the decimal number of systems, let's say we add 5 and 5, we know that the result is 10, sorry. The result is 10, and 5 is only one decimal digit, and the other 5 is also one decimal digit, right? And adding them, we get a result that is 1 and 0, which is 10, which is not a one decimal digit, but two decimal digits. So this is kind of the same thing in binary. We can have one signal A. By signal, I mean something like this from our previous class. This one bit is one signal and another signal. So we need to create a circuit, a combinational circuit that is able to add this and the second one. And since it's addition, we have a potential of having a carry. So it's going to also present to us a carry bit, which is carried over to the other that digit. So in total, we'll have 3 digits and so on. If we chain a lot of half adders, we can get full adders and so on. So today we are going to see how we're able to create these circuits that are able to add signals, and so stay tuned. The level says we measure the universe with numbers, so your machine must learn to count. Okay. Treat the inputs as 0 or 1, depending if they are red for 0 and green for 1, which is just the binary number system, true or false, and add them together in binary such that the result is either 0 or 1. Okay. With normal addition, if the result cannot be described with one digit, set a carry. Okay. So as we can see in this level, we have 2 bits, right? We have this and this, and we need to add them together. So let's assume they've told us that we should assume that this is 0, and let me see that again. Oh, green is 1 and red is 0. So right now we have 0 plus 0, which is still 0, right? So let's start with an OR gate to add this. So 0 plus 0 gives us 0. And if we have 1 plus 0, 1 plus 0, which is this, gives us 1. Okay. And also 0 plus 1 still gives us the same, so which is okay. And 1 plus 1 should give us 1, but I think we should have a carry bit. So to do that, to say 1 plus 1, which is 2, we need to do this to check only if both of them are true. That's when we get a carry. So I think that's a half adder. So let's start with this. 0 plus 0 is 0. 1 plus 0 is 1, which is same 1. And yeah, and the desired sum is 1, which is still okay. And 0 and 1, which is 0 and 1, gives us the same sum as 1. But having both of these as on should give us a carry of 1. But I already see the issue is that we still get 1 over here, which means that if both of these are on, we need to negate this. And by negating that, we can just probably add an AND gate and not an AND gate. Is it an AND gate? I'm thinking an exclusive OR, meaning that we can't have a carry when we have a sum. We only carry when something has gone over, and since we only have 2 digits, we only have a carry when this is 0. So an XOR should be able to do it. And yeah. So again, let's start our first test. We have both of them as 0. And the desired sum is 0, which is here, and the desired carry is 0. If we add 1, that means that if we have 1, now we can see that the signal flows through here, and we are able to get our sum as 1. And even if we invert it, still get the same thing. But when we have both of them as 1, it's when we now get the carry but not the sum, which is okay in this case. We have both of them, we have a carry and not the sum. And this is how to create a half adder. Let me see. Yeah, it's made up of an XOR and an AND gate. And is that the same thing I have? Yeah, but I have an extra OR gate, which I don't know, maybe it's not necessary. But the circuit works for a half adder. A clean adder, according to Google, is it looks something like this. We just have the XOR and the AND gate. And this is able to produce for us this is still an XOR gate, so that means that my version was not really sufficient enough, and efficiency is really important since these circuits are going to be created using physical things, actual transistors which cost money. And so if you don't have a proper design of these kinds of circuits, the most efficient designs of these circuits, like the one we had before, you'd see that we had an extra gate that wasn't really doing anything important, and so we want to get the most efficient version of our circuit. And in this case, the most efficient half adder circuit is this in this case. So the bottom line is that efficiency is also kind of important in designing the circuits that perform a particular thing you need. And the next level after creating a half adder is delay lines. Let's see what this is all about. This level introduces the delay line component. This component, it takes input, it takes its inputs and outputs it one tick later. As we said before, a tick is for a computer to perform things. Usually an electric circuit is mostly just if there is power input and an output, then we have our circuit in between. As long as that input circuit is maintained, nothing is going to change unless we have things that are changing based on things. And that's why a computer is basically made up of tiny little billions of switches which are able to help us do things. That's including making calculations and doing a lot of things. So a tick is important in such a way that a computer cannot work without cycles. They are called clock cycles, which means in this case it can be like a tick. Like one clock cycle can be a tick, like something that is able to move an electrical, is able to cause an electrical change within that whole system. So a computer, as we can see, like here, as we navigate and test our outputs, we are able to navigate through the changes. So that navigation is moving across those ticks. And this level is able to, the component that we're talking about today, which is a delay line, is able to if I input green right now, it's not going to output a green immediately until the next cycle, until the next tick or the next change. So it's like something that's delaying, like it's a bit behind. Let's see what this level is based on the example. We are told that construct a circuit that outputs the same as the input. What do you mean? Construct a circuit that outputs the same as the input, just delayed by 2 ticks. Okay, that means that if I turn on this, I move to the next, then make another change, then move to the next, then make another change, that's when we get this signal as green. Yeah. So we already have a component that is able to delay. So right now I have an input as green, but it outputs red, which is false. If we move to the next tick, if we move to the next tick, then this will be green. Like right now we have our input here as green, as red, as false, and our output as false. So if I move 1 tick, we have input as false, output as false. I move another tick, input as true, but output still as false, and move next again. Now we have another one. We're supposed to get output as false, and output as false, which is okay. And again, here our next one is input as false, and now the first signal that we created here on our second tick has now been delayed over here, and I had a second delay, and now it's getting to the output on our third delay. So by chaining these delay lines, we are able to kind of store some signal that we want to be able to use it later. So as we see in the future, this is just a brief introduction to how memory is able to be created using just these circuits, and how we are able to preserve some bits that we want in order to do a lot of things that as per now we can't preempt it, and we'll just wait and see how it goes. And if I run it all, yeah, it works, but let me just run it step by step. You can see the signal propagating to the end, another one propagating little by little, and again. And that's the level of delay line. And this should be our final class for today. The level is double the number. I'm not sure what it's about, but let's see. It says the input and the output of this level are using bytes instead of bits. As we said that a bit is just one signal like this, and then we have a word A word, yeah, a word is a natural unit of data processed by a processor, so it's not a word. We have a bit. We have, I know a byte is 8. A byte is 8 bits. And but we also have 4 bits. There is a name for 4 bits, which I'm trying to look at. And yeah, I needed to confirm it. It's enable, consists of only 4 bits. And now we are going to deal with a byte which is essentially 8 bits. So we are told the input and the output of this level are using bytes instead of bits. So right now, if you see, this is a byte. One of the 2 new components you're given takes a byte and splits it into bits, and the other does the opposite. Using those components, figure out how to double the number of inputs to 127. What does that mean? Okay, we do have one component which is called a byte splitter, and we have a byte maker. So we're told a byte is 8 bits. If you see this has 8. If you count these pins, they are 8. Their outputs. That means that if I input any number, which is, let's say, 25, we can see the output that we get. This is binary for that 25. It's 1 from here 0 0 0 1 1 0 0 1. So we are told we want to double the number, so I'm guessing multiply. And yeah, I think I did this level, and from what I remember, to double a number, we just move the signal this way. We have, this is a 8-bit maker, which can take just any 8 bits representation and output a byte to this kind of byte output. So by doing this, we're able to, by, I think it's called shifting, we're able to multiply, or rather double the number. So as we can see, the output should be 50 essentially, and that's what we get. Yeah, it took me a bit of time, but yeah, I really don't know why it works, so you can leave a comment on why this works. But this is a circuit to double the number. Okay, I think it makes sense. I think I understand a bit, since we have this bit, to be able to double it is 1 times 2, and 2 we output to 4, which is the double of it. 4 we output to 8, 8 we output to 16. Yeah, because essentially we would have this 8 going to 8, and that output would be the same 25. But now we are shifting it, and now this goes 16 goes to 32, and the resulting binary is the double of that number. So this is how we double the number, and we can test it. And yeah, in our next class we're going to see how we can construct a full adder. Full adder is essentially just the same half adder we did earlier, but now kind of chained together to create something that's a half adder. I guess it does 8 bits kind of additions, so it's has a bigger kind of inputs, but essentially underlying it does the same thing as the just 2 bits adder. And yeah, so see you in the next class. Bye.